shrimp. Go to the grocery store, and shrimp are packaged kind of strangely, right? There's 41 to 50 count shrimp. They're sold by the count. Does that mean that there's 41 to 50 shrimp in that package? Not necessarily. The count indicates the size of the shrimp. That 41 to 50 count means that there are between 41 and 50 shrimp in 1 pound. So if you had a pound of shrimp, you'd have between 41 and 50 shrimp. If you have a smaller count, fewer shrimp per pound, that means that the shrimp are larger. So the big tiger prawns might have a 10 to 15 count. So in 1 pound, there'd be 10 to 15. So each of those shrimp could weigh as much as a tenth of a pound. Maybe that's why they're called prawns and not shrimps, because they're not so small anymore. But we can count shrimp by weighing them. So if you got 2 pounds of 41 to 50 count, there's a typo here. It's not 84, it's 82. 2 pounds of that kind of shrimp should have between 82 and 100 shrimp, right? Because the smallest number it could have would be 41 in each pound. So 2 times that would be 82. And the most that could be in a pound would be 50. You're still getting a pound, or in this case, 2 pounds of shrimp. But the question is, how many pieces are there? So we use a similar idea, but much more precise for atoms. Any questions about shrimp? So chemists often want to know, or need to know, the number of atoms in a sample. Why do we care about this? Because chemical processes happen between individual particles. So 2 hydrogen atoms combine with 1 oxygen atom to form 1 molecule of water. Those are exact numbers. It's always 2 hydrogens to 1 oxygen. If it's something else, then it's not water. And you can't have 2.5 hydrogens. It's 2, right? So when we want to know atoms, the number of atoms in anything of a normal size, meaning you could actually see it, there's way too many to count, and they're too small to count, so we can't do that. So like with shrimp, we count them by weighing. In the retail world, there are lots of things that you buy where you don't just buy like 1 egg, you buy 12 eggs at a time, right? And so we have a name for 12 objects. It's a dozen. That's a counting unit. And dozen can be used with anything. We're familiar with a dozen bagels, a dozen donuts, a dozen eggs, but you could have a dozen elbows, right? That would just mean 12 elbows. It's just 12 of something, right? It's a counting number. Another counting unit that isn't maybe so familiar is a gross. Ew. It's gross. A gross is a dozen dozens, 144. So like little sample vials and stuff are sold by the gross. It's a dozen dozens. There's another counting unit, a ream, used for paper. How many is that? It's 500 actually. So a ream is 500 sheets of paper. Depending on the quality of the paper, that ream might weigh more or less. It's just sold by the count, right? So these are nice units and everything, but they are too small for atoms. So we have to have our own dozen, and the chemist dozen, and it is the mole. M-O-L-E, not a little rodent who lives underground, not a tasty sauce, a mole, the chemist dozen. Very short word, and yet it still has an abbreviation, M-O-L. Don't know why, but it does. So a mole is the amount of stuff that contains 6.02214 times 10 to the 23rd particles. So instead of 12, it's this weird number. This weird number has a name. It's called Avogadro's number. And so there's a joke that I can never remember that has to do with guacamole There's a mole, and it's avocado and Avogadro, and I really need to look that one up because it's great, but I can't remember it. You can imagine, though. So 1 mole of anything is 6.022 times 10 to the 23rd things. Just like 1 dozen is 12 things. Okay, in your previous chemistry class, you should have used a mole, but students can be successful in a chemistry class and still just not really understand what that whole mole thing is. It's just a very big dozen, okay? That's all it is. A mole of substance is a useful size of substance, right? So here we have an illustration of 22 pennies. 22 pennies is approximately 1 mole of copper atoms. You can hold those in your hand. Big enough to see, small enough to hold. Nice amount. A tablespoon of water is approximately 6.022 times 10 to the 23rd molecules of water. Okay, useful. So now I have to tell you a personal story, just because. So, you know about Pi Day? March 14th, 3.14. Mathematicians have fun with Pi Day, right? And then there's May the 4th for Star Wars fans. Chemists have Mole Day. Mole Day is October 23rd, 10:23. Technically, from 6:02 a.m. to 6:02 p.m., right? Just those 12 hours. But that's Mole Day. So I'm a chemist. My husband's a chemist. Our 4th child was born on Mole Day. It was so cool. So we call him our mole baby. And we actually looked at each other and said, should we give him the middle name Avogadro? No. So we didn't. We named him after a video game instead. His middle name is Yoshiaki, after Yoshi's Story, Nintendo game. And what's even cooler about him is that he weighed 10 pounds, and he was 23.5 inches long. It would have just been like too perfect if he'd been born at 6:02 a.m. or 6:02 p.m. It was more like 8:30 p.m. You know, I did what I could. There's just a limit to what can be done. But that was just a really fun thing for a couple of chemists. My mole baby. Where did that number come from? So the value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. Now, that weird definition should sound vaguely familiar. An atomic mass unit is 1/12 the mass of a carbon-12 atom. So here we have another definition based on carbon-12. So 1 mole of carbon-12 atoms weighs 12 grams. So this gives us a relationship between mass and numbers of atoms. So if we had 12 grams of carbon, we could know that we had 1 mole of carbon atoms. So this allows us to count atoms by weighing them. So we'll do some examples with this. So we need to be able to convert between moles and numbers of atoms. And this is the same as converting between number of eggs and dozens of eggs. So imagine you go to Costco, maybe before Easter, and you buy 5 dozen eggs. They're all bundled together, right? How many eggs is that? 60. How'd you do that? 5 times 12. You're geniuses. It makes sense to you, right? You know what a dozen is. You can picture the eggs, and you realize, I need to multiply by 12. I'm not going to divide by 12, right? Or I'm not going to take 12 and divide by 5 or do anything crazy like that. I think of that as like walking down the sidewalk, a regular sidewalk that has grass on both sides. Do you have to think about walking down the sidewalk and not falling off? No. Now imagine that sidewalk is a bridge over the Grand Canyon that has no railings, that gives me the heebie-jeebies. I don't even like to stand too close to the Grand Canyon because I feel like I might suddenly lose my impulse control and throw myself over. So I'll just look from over here, thank you very much. There's also a sign, we went there with a 3-year-old and a 5-year-old. There's a sign that says most of the people that were injured did not follow the rules posted, something like that. Most of them. That means at least one person was doing everything they were supposed to do and they fell in anyway. It's just like, it's a beautiful place. I have no desire to go there again. It's this really, really big, beautiful hole. Anyway, you can imagine walking on this sidewalk without any railings across the Grand Canyon. I couldn't do it because now all of a sudden I'm thinking about it because the consequences of stepping wrong are death, right? So it's hard. And yet, if you had the illusion of grass on each side, no problem. You could run down the sidewalk, right? You wouldn't fall off. What's the difference? It's in your head. It's all in your head, right? So you can convert between dozens and eggs like there's grass on both sides of the sidewalk. But when I start throwing in moles and atoms of titanium or something, all of a sudden it's the Grand Canyon and you freak out. Okay? So it is the same kind of calculation. You can do it, and so you just need to get around the fear in your head or whatever it is that's doing it to you, okay? Might take a little practice, but we can do it. So eggs in dozens, a dozen eggs is 12 eggs. It's never one egg is 12 dozen eggs, right? A mole, it's not where I'm pointing. A mole, there we go. One mole is this many number of atoms or ions or particles, right? Could you have a mole of eggs? You could. They wouldn't fit in Costco, though. You could have a mole of eggs, 6.022 times 10 to the 23rd eggs. So when we convert, we can put mole on top and the number on the bottom, or the number on top and the mole on the bottom. But it's always one mole and that many atoms, just like it's always 1 dozen and 12 things. Okay? Just don't fall into the Grand Canyon. So let's do an example. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? We're just converting between atoms and dozens of atoms. It's just that we use a different number than 12. So I'm starting with atoms, and it's asking how many moles. So we're just following that pattern. I'm at the mall. I need to find out where I am on the map, and I need to figure out where I'm going, and then I make a path to get there, and I follow the path. So this is where I'm starting. This is where I'm going. How do I get there? I can do this in one step using Avogadro's number. And especially at the beginning, it can be helpful to actually write that down. So 1 mole equals 6.022 times 10 to the 23rd atoms. Now, Avogadro's number is known to more than 4 significant figures, but usually we just use 4 because it doesn't mess things up. So just remember 4, 6.022 times 10 to the 23rd. I'll probably give you that on an exam, but if you do your homework, you'll have memorized it by the time we get there anyway. So now I have my dimensional analysis path, and all I have to do is follow it. So 2.80 times 10 to the 23rd atoms. I look at my path and I have 1 arrow. That means I have 1 fraction. It goes atoms to moles. See, one of the, question?
Is it 10 to the 27th?
Yes. I did that to see if you were paying attention. No, I didn't. This is 22. Yeah, always good to check that you copy the number down correctly. One of the things that's good about having 2 sections of the same class is, especially for you guys, the second section, it comes out better. But the bad thing is I can't remember if I told you stuff or if I told the other class stuff. Did we talk about Dora the Explorer? No, okay, that was the other class. You guys know who Dora is, right? She's got a movie out now. When I do this, I'm always thinking about Dora the Explorer. Because, she always needs to get somewhere, and then she's not sure how to get there. And who do you call when you don't know which way to go? The map, right? And the map comes out and does this little song and dance thing. And then they look at the map and they say, well, first we're starting here with the atoms, and then we need to go over here to the moles, right? But usually it's like 3 or 4 steps. And then they chant it together. Atoms to moles, atoms to moles, atoms to moles. So that's what we're doing. Here's the path that the map told us, right? And then here we're going to chant atoms to moles, right? Yeah, it's dumb. And you do that. You just write them all down on the numerator. So some of you are still iffy on this dimensional analysis thing. It really, really, really is important. And so it's not too late to figure it out. So I followed the path, and now to get rid of atoms, I put them down here. And then they're going to cancel. That was a little too much canceling. I pushed I don't know what button I pushed. There, atoms. I still want to be able to see it. I get all the units in there. And then I put the numbers in. And the units tell me where to put the numbers, and there is so much less thinking. Because sometimes we overthink things and we end up screwing it up, right? Like walking on the sidewalk. You start thinking about it too much and you can't do it anymore. So we're just going to follow what the units say. So mole is up here, and I look at my conversion relationship here, 1 mole. I'm not going to think about it. I'm just going to write 1 with mole. Avogadro's number is with atoms, and so I'm going to write that here in the bottom with atoms. Easy peasy. Okay, now we have to communicate correctly with our calculators, which should be a simple matter, and yet it is not. We have to use scientific notation here because there's no other way to get Avogadro's number into your calculator. It's got too many digits. So your calculator, you should all have a scientific calculator, and it will have an EE button, an EXP button, or there are some that have, I made that wrong, a times 10 to the X button. If you have one that just has this times 10 to the X button, and that's different than 10 to the X. It says times 10 to the X. 10 to the X is anti-log, completely different. If you have a calculator with this instead of EE or EXP, I would encourage you to get another calculator, okay? You can do everything on that calculator, but it's going to require the use of parentheses like almost all the time, and it's just confusing. So if you have one of those, we'll talk in private. I'm not going to talk about those right now. So either of these buttons does the same thing. That stands for times 10 to the. So if I want to enter this number into my calculator, let's put a different color in here. So I'm going to punch in the 2 and the decimal point 80 EE 23. As I push EE, I think times 10 to the. It's an abbreviation. Okay? It makes everything much easier. Yes, you can get the number into your calculator other ways. But when you use the EE or EXP button, your calculator understands this is a single number. And so then when you divide by something, it's not going to do crazy things. Okay? So get your calculator out. And even cell phone calculators, if you, like on mine, if I tip it sideways, or you tell it, it'll show you a scientific calculator and it'll have this. So 2.80 EE22 divided by 6.022 EE23 equals. And so the answer I'm getting is a small number. I should have 3 significant figures. I'm going to write down 2 extras. The unit is mole, and then I'm going to round it. And my final answer is 0.0465 moles. Now, a common wrong answer is 4.6496 times 10 to the 44th power. That's a wee bit different, right? How does that happen? That happens if when you divide by this number, your calculator doesn't understand that you meant that to be one number. And what your calculator does, it divides by 6.022, and then it multiplies the whole mass by 10 to the 23rd, and you end up with an extremely wrong number. Yes?
I don't know if it's helpful or not, but if you have this model of calculator, it has Avogadro's number programmed into it as a constant.
Seriously?
Second, constants.
Sweet.
Yeah.
That's my favorite calculator. I just learned something new.
Second, and then parentheses there, the constant.
So the TI-36X Pro has a bunch of constants in it, and so you can actually just pull it up that way. I probably won't do that because it's in my head. But very good to know. Very good to know. I'll have to investigate the rest of those. Make sure that you can get your calculator to give you this answer. You having trouble? Yeah.
Whenever
So that's converting between moles and numbers of atoms, but we need one more factor, the mass of 1 mole of atoms. So this is called the molar mass. The molar mass is the mass of a mole. The atomic mass is the mass of an atom. Okay? These are descriptive terms. So an element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. So if we look at aluminum on the periodic table, the number under it is 26.98. That is the mass in atomic mass units of one atom, the average mass. It is also the mass in grams of 1 mole of aluminum. And that's not some weird coincidence. We set it up that way. That is why Avogadro's number is what it is. So that the atomic mass in atomic mass units is the same number as the molar mass in grams. So that number does 2 purposes. So 1 mole of aluminum, Avogadro's number of aluminum atoms, 26.98 grams. 1 mole of carbon, also Avogadro's number of atoms, only 12.01 grams. 1 mole of helium, Avogadro's number, only 4 grams. Why does the same number of helium atoms weigh less than aluminum? Because each atom is smaller, right? 1 atom of helium weighs 4 atomic mass units. 1 atom of aluminum, did I say aluminum? Helium, this is helium. 1 atom of aluminum is almost 27 atomic mass units. So if you have a dozen of them, they're going to weigh more. If you have a chemist dozen of them, they're also going to weigh more. So the molar mass is the conversion factor between the mass in grams and the amount in moles. And so this number, this molar mass, is on the periodic table. Another reason that we keep looking at the wall. So the number under the element symbol in grams is equal to 1 mole of that element. And so we can put grams on top and moles on the bottom, or we can flip it upside down. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So we write down the number, 35.8 grams. Now we're getting to the point where sometimes it's important to say grams of what? So this is grams of copper. And what are we trying to find? The number of moles, still of copper. How do we get from grams to moles? Just use the molar mass, right? So one step. So here's Dora, grams to moles. 35.8 grams of copper, one arrow, one factor. Grams to moles, and grams goes down there. Cross that out. Units are working out. All the units in place. Now I need the number. Anytime you got grams to moles, it's most likely going to involve the periodic table. So we look at copper, and underneath copper it says 63 point, I'll just use the whole one, 63.546. So we could write that down as 1 mole of copper is 65, can't remember, 546, 63, yeah. I don't know why I have such a hard time with that one. It's the mass of 1 mole. So the number is going to be with grams. So I put this number on the bottom, not because I'm supposed to divide by the molar mass, but because that's where the unit is. That's where gram is. And I have 1 up here. I'm not thinking I multiply by the molar mass or I divide by the molar mass. I put the units in there and they tell me what to do. So 35.8 divided by 63.546. And as I'm writing this unrounded number down, I think ahead, my ultimate answer is going to have 3 significant figures. So 5, 6, 3, there's my 3 significant figures. Write down 2 extras to avoid rounding errors. And then 0.563 moles of copper. Any questions? .563. Okay, so now we can put all the pieces together to count atoms by weighing them. So there's the process. You've got the mass of the sample. You convert the mass to moles using the molar mass, and then you convert moles to number of atoms using Avogadro's number. So this is the path, grams to moles to number of atoms. Each of these steps, we have to know the relationship between those 2 units. So the relationship between grams and moles is the molar mass of the element. Between moles of an element and the number of atoms, this is always the same. It's Avogadro's number. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat is 0.20 grams. So here, the first example does not exactly follow that path, right? Because that wouldn't be any fun. Just going to approach this with dimensional analysis. So I read the question. I maybe don't know exactly what I should do. I'm going to pull out the numbers and write them down with their units. So I've got 1.3 carats. And I've got in parentheses 1 carat equals 0.20 grams. Okay, great. I've got 2 things, not sure what to start with. Let's figure out, what am I trying to find out? How many atoms? So over here, I'm going to try to find atoms of carbon. And I have to figure out how to get from carats. Maybe you've never heard of that. It's a unit that jewelers use. Get from carats to atoms. Well, this thing in parentheses is a conversion factor, right? It even looks like one. 1 carat is 0.20 grams. So I'm probably going to start with this. This is going to be my starting number and not this equation. So 1.3 carats. Could I convert carats to grams? Yeah, they handed it to me, the relationship. I can go to grams. And then from grams to atoms. Okay, there's something missing in the middle. If you're not sure what to put in the middle, try moles. There's a TV show called Malcolm in the Middle. Moles in the middle, right? We often find in our calculations that moles are going to be in the middle. And sometimes there's two different kinds of moles in the middle. So that can just be a place to look. So could I go from grams to moles? Sure. Can I go from moles to number of atoms? Yeah. So there's my path. That's the hard part. And you may feel dumb doing it, but write the path out. Unless you're just whizzing through these assignments, homework and stuff, you're just like, oh yeah, I got this. If you're not one of those people, write the path. Okay? It's like, write the path, right? It gives you something to follow. It makes it easier. And then after you've done it a few times, you won't have to do it anymore. But until then, you'll just make a mess of your calculations. Okay. 1.3 carats. 1, 2, 3 arrows. 3 fractions. And then here's Dora chanting with the map. Carat to gram to mole to atoms. Carat to grams to moles to atoms. And one of those is like the scary troll, one's the snowy mountains. And I just copied it down. And then the previous unit comes down here. So it'll go away. And grams comes down here. And moles goes down there. All the units. Now, I just put the numbers in so they match up. So I've got this guy, 1 carat, 0.2 grams. Here I've got a factor with grams and carats. Well, the number with carat is 1, and the number in front of grams is 0.20. It's kind of a sad-looking one. Grams and moles. Where do I get that? Periodic table. This is carbon. So we look at carbon on the periodic table, and it's the mass of 1 mole. So it's 1 mole of carbon weighs 12.01 grams. I rounded it. And over here, atoms and moles, this is Avogadro's number. And sometimes students put Avogadro's number in the wrong place. Atoms are like eggs. Moles are like dozens. So where do I put the 12? Eggs. And 1 dozen, right? Because an egg is not 12 dozen eggs. So I'm going to do the same thing with my Chemist dozen. I'm going to have 1 mole and the number with atoms. It's just not 12. Not even close. There we go. Get out the calculator. Make sure you do scientific notation correctly. 1.3. Multiply by the top, divide by the bottom, and as always you can skip the ones because it doesn't change anything. And I'm thinking about significant figures because I'm surprised I don't have dreams about significant figures. We should have 2 here, right? 1.3, there's 2 significant figures. I'm going to write down 2 extra digits. And then on my calculator, there's a whole bunch more digits, and then it says a little E22. And sometimes students just like, I don't know, just leave that off. Don't leave that off. That's super, super important. That's math language. If you wrote that on your paper, I'd know what you mean, but that's what the calculator says. It's calculator language. We need to use human math language. So instead of the EE, I'm going to write times 10 to the 22. Some calculators have fancier displays and will actually show it to you. Others, like mine, do not. So it's that many atoms. And then I can round 1.3 times 10 to the 22 atoms of carbon. Is that a reasonable answer? Yeah. Anything that's large enough to see is going to have a ginormous number of atoms in it. What if I got 0.7 atoms? Can you make a diamond out of 0.7 atoms? Can you even have 0.7 atoms? That's like 0.2 children, right? Average family has 2.2 children. What does that 0.2 child look like? There's no 0.2 child. You can't have less than an atom. You have no atoms or one atom or more. And if you get less than an atom, you've usually got your number in the wrong place, or you did scientific notation on your calculator wrong, something like that. Anybody have any questions?
So we can have 1.3 something, but we can't have points.
Yeah, you can have 1.3 times 10 to the 2 atoms. You actually will never end up with like 1.3 atoms either, because 1.3 children.
So it has to be some type of number.
Well, it needs to be, when we do atoms, it's always going to end up to be a really big number. There's going to be this times 10 to the something. And when you end up with moles, sometimes you'll have like 0.5 moles. Well, can you have half a dozen? Sure. Right? So you can have a fraction of a mole, but you can't have a fraction of an atom. (1.3 times 10 to the 22). Okay, and here's some just kind of blow your mind stuff. Avogadro's number of pennies would cover the Earth's entire surface to a depth of 300 meters. That's the length of 3 football fields tall. Pennies covering the entire planet. Is that a big number? Yeah. We just can't even get our minds around it. It's way bigger than the national debt. So if you had Avogadro's number of something smaller, like a grain of sand, still mind-boggling, it would cover the state of Texas, a very large state, to a depth of several feet. If you counted 24 hours a day as fast as you could for the rest of your life, you would not be able to get to 6.022 times 10 to the 23rd. And then there's the number written out in decimal form. That's a heck of a lot of zeros. So one more problem here. And this is another critical thinking problem solving. So in general chemistry, you should be able to take the pieces that you've learned and put them together in a way you haven't seen before. And there will definitely be at least one exam problem that'll be something on the order of this. It won't be this, though, because I'm going to show you how to do this one. But it'll be take the pieces that we learned and put them together in a new way. And this is challenging for a lot of people, but everyone can get better at it, okay? So that's the goal, is to become a better problem solver. A titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. Okay, not sure where to start. Write down the numbers. I'm going to do that. 2.86 times 10 to the 23rd atoms. We might need to know what kind of atoms. These are atoms of titanium. And then they give me a density, 4.50 grams per cubic centimeter. And that's how people tend to write it down, because that's how it was written in the problem. Your brain often doesn't recognize that that's a fraction. So don't write it down like that. Make it a very obvious fraction. Because it's 4.5 grams per cubic centimeter, per 1 cubic centimeter. Does that look like a conversion factor? Yeah, it does. Okay, so what are we trying to find? The edge length of a cube. Somehow geometry has gotten in here. Let's draw a picture. Drawing pictures often can be helpful, even if they are really ugly and barely recognizable. I am reasonably good at drawing cubes, though. Kind of a cute little cube. So we want to know how long one of the sides is. A cube is a three-dimensional object where the lengths of the three dimensions on the sides are the same. What letter do geometry people tend to give that? L, right? We'll call it L. So we'll call this L. And we got atoms, and we need to get to the length of a cube. So a lot of the problems that we've done are just dimensional analysis. But sometimes there's dimensional analysis and something involving an equation. Do you know of an equation that would relate the volume of this cube to its edge length? Yeah, the volume equals L cubed. So we should be able to solve that for L. So I have L cubed. I need to uncube it, right? So I'm going to take the cube root of this side, and I'm going to do the same thing to the other side. And the cube root of the cube is just the thing. So L is equal to the cube root of the volume of the cube. Like, well, that's all nice, but how does that help? Well, the equation says if I knew what the volume was, I could find the length, right? Here I've got a number of atoms. Could I possibly figure out the volume of those atoms? Maybe. Let's see if we can get there. So here I've got cubic centimeters. So maybe let's try to aim for the volume in cubic centimeters, right? I don't know how many atoms are in a cubic centimeter of titanium, but they did give me the density. The density relates grams and cubic centimeters, right? So if I knew the mass, I could get to the volume in cubic centimeters. So I'm working backwards here. And how do I get from atoms to grams? I'm missing something in the middle. Moles. I could go from atoms to moles using Avogadro's number, and moles to grams using the molar mass that's on the periodic table. Now we've got a plan. Okay? Coming up with the plan is the hardest part of this problem. That's what messes you up. That's what causes you to text me. I don't even know where to start. And it's good that you ask me that, because then I can give you, it's like, well, what about this? And get you started. And then at some point, you're like, oh, I know how to do it now. So that's the hard part. And that's the part you need to work on getting better at. So now that we have our map, our path, we just follow it. 2.86 times 10 to the 23rd atoms of titanium. There's 3 arrows, 3 conversion factors. And Dora and the map are chanting atoms to moles to grams to cubic centimeters. Atoms to moles to grams to cubic centimeters. Then I put the units in here so they are going to cancel out. And moles down here, and grams down there. There's a density involved here, but I'm not going to use the density equation. Everybody wants to do that, and you can do it that way, but students screw it up a lot. It requires a lot more thinking, and then you're overthinking it and you're falling off the sidewalk, right? So don't do it. Just dimensional analysis. We've got all these units in here, and they're going to tell me where to put things. So here I've got this density. Grams and cubic centimeters, that's going to be over here where I've got grams and cubic centimeters. 1 cubic centimeter, so I put 1 with cubic centimeter and 4.5 with grams. I don't have to think about multiplying or dividing or anything. It's just put the number with the units. Moles and atoms, this is like dozens and eggs, right? So 1 mole, Avogadro's number of atoms. Then the one in the middle, grams to moles, is hiding on the periodic table. So we find titanium right up there. 1 mole is 47.867. I don't have that one memorized, so I'll just use all the digits on the periodic table. So I get out my calculator. So you should get out your calculator and make sure this works. Anybody get that number? 5.0518 cubic centimeters. Is that the edge length of the cube? No, I'm not quite done yet. I had figured out that I needed the volume so I could plug it into this equation. So the edge length is going to equal the cube root of 5.0518 cubic centimeters. And your calculator should be able to do this, and if you have trouble, ask me in lab. On the TI-36X Pro, what I do is I press the 3, and then I press, there's a root button that has a square instead of a number or anything. And then I put the number 5.0518 inside and press equals. So 1.7158. The cube root of cubic centimeters is centimeters. And so when I round this, I get 1.72 centimeters. Any questions? A good way to practice problem solving is to pull up this slide and do this problem without looking at your notes. Because chances are good that you're not going to remember exactly how to do it. And so then you'll have to start figuring it out. And then if you get stuck, you can go look at the video and I'll talk you through it again. 1.72 centimeters.